In this continuation of section 2.2, we will talk about solving systems with the inverse and also properties of the inverse. We've just finished talking about the inverse and what we know about the inverse and the identity. So now the question is, why do we need the inverse? And it is for this purpose right here. Theorem 5 in your textbook says if A is an invertible n by m matrix, then for each b in Rn, the equation Ax equals b has the unique solution x equals A inverse b. What does that mean? So before we talk about proving it, what does it mean? Why is it important? Well, previously, we've done a lot of solving of systems in the form Ax equals b. When we solved those, we created an augmented matrix using the matrix A and the vector b and solved for x. And now what I'm saying we can do is we can find x by taking the inverse of A multiplied by vector b, and that's going to give us our unique solution, x. So let's talk about the proof. I'm starting with Ax equals b. I need to prove that the solution does in fact exist. So let's do a little bit of left multiplication by the inverse of A. So the inverse of A times Ax is equal to the inverse of A times b. The inverse of A times Ax, I'm just going to regroup these by the associative property. Inverse of Ax equals A inverse b. While the inverse of A times A, we've talked about that property, is just the identity. So the identity x equals A inverse b. And that just means that x equals A inverse b, which is what we were told. What else do we need for this proof? Well, we need to prove that it is a unique solution. So we're going to assume that that AU is equal to B and that U is equal to A inverse B. So if I take A inverse times AU equals A inverse B, then I can again regroup A inverse A. Sorry, my handwriting's getting a little sketchy. A inverse B. Again, this is the identity, A inverse B, and that's just U equals A inverse B, and therefore it is indeed unique. Now that we have learned the theorem and proved it to be true, let's go ahead and solve the system using the inverse. So just as a reminder, we want to write our system as a matrix equation. And then we know that the solution to our system is going to be the inverse of A times B. So as a reminder, this is our matrix equation. 3, 4, 5, 6 is matrix A. We're multiplying that by x1, x2, x1, x2, which is of course x, and B is 3, 7. So far, so good. Now, in order to solve, I'm going to then take A inverse times B, and this guy over here is B. So let's start by finding A inverse. Now, if you'll recall, we just learned how to find A inverse in our last video. And our last video says if A is A, B, C, D, then A inverse is 1 over AD minus BC multiplied, and that first diagonal is going to change location, and the second diagonal is going to change signs. Sorry to sort of squeeze that all in there, but I've got a lot to fit on one little slide. So let's do that. Let's go ahead and take A inverse. So I'm going to take 1 over 3 times 6, which is 18, minus, don't forget that it's minus, 5 times 4, which is 20. And then I'm going to change the location of 3 and 6. So I'm going to swap those. And I'm going to change the 4 and the 5 into negatives. So I'm going to continue this math to find the inverse of A. So that's 1 over 18 minus 20 is negative 2. So my fraction is negative 1/2 times 6, negative 4, negative 5, 3, which means my inverse is negative 3, 2, 5/2, negative 3/2. So to find my solution, x is going to be found by multiplying A inverse, which I'm just going to copy from the work I just showed, multiplied by B, which is 3, 7. And when I do that math, I should end up with the correct solution. So again, we know how to multiply matrices just fine. I'm going to switch colors here. And I'm going to start with negative 3, 2. So negative 3 times 3 is negative 9. Plus 2 times 7 is 14. And then 5/2 times 3 is 15/2. Plus negative 3/2 times 7 is negative 21/2. And if I simplify, negative 9 plus 14 is 5. And 15/2 plus negative 21/2 is negative 6/2 or negative 3. So that's my solution to the system. And if they said solve the system, I could be done right there. Now keep in mind, I didn't show that I multiplied each side by A inverse, but I don't have to do that because of Theorem 5. So now let's go ahead and verify this using our row operations. So if you'll recall, what we've done up to this point is written 3, 4, 3, 5, 6, 7 as an augmented matrix. And then we're just going to do some row operations. And ideally, we'll end up at 5, negative 3. So let's see how we do. I'm going to start by dividing the first row by 3, which is the row operation of multiplication, by 1/3. So 1, 4/3, 1, nothing happened to the second row. My next step is I need to get that 5 to be a 0 because we need reduced row echelon form. So I'm going to take negative 5 times my row 1 and add it to row 2. So row 1 remains exactly the same. Row 2, negative 5 plus 5 is 0. Negative 20/3 plus 6. 6 is 18/3, so negative 20/3 plus 18/3 is negative 2/3. And then negative 5 times 1 is negative 5, plus 7 is 2. I'm going to continue by turning that negative 2/3 into a 1 by multiplying by negative 3/2. So my first row will remain the same. My second row, if I take everything times negative 3/2, I'll of course get 1 here. And then 2 times negative 3/2 is negative 6/2 or negative 3. And I'm almost where I need to be. I'm going to take my second row times 4/3. So I'm going to keep that second row the same. I'm going to multiply it by negative 4/3 and add it to row 1. So 0 plus 1 is 1. Negative 4/3 plus 4/3 is 0. And then negative 4/3 times negative 3 is positive 12/3, which is positive 4, plus 1, which is positive 5. And so, notice I have my result of 5, negative 3 is x, which is our solution. Here's one for you to try on your own. So again, follow the same steps we did in the last question. You do not need to check this one with row operations. So just solve the system using the inverse. Feel free to plug those values back in to check your work if you're nervous about it. Otherwise, when you are ready, press play to see how you did. All right, so the first thing I'm going to do is recall that this is an equation in AX equals B form. x1, x2, and then b is 7, 1. So it's always good to remember that that is where we are to begin with, and then to solve, I know that I have to find A inverse times B. So this is A, this is X, this is B. A inverse is 1 over 3 times 3, and I'll go ahead and show what I would ask you to show, 3 times 3, minus 2 times negative 1, and then 3 and 3 would switch places, which you can't really tell, but we did, and then negative 1 becomes positive 1, positive 2 becomes negative 2. So that's going to be my inverse, and I'm going to multiply that by 7, 1. I'm going to do some simplification. 3 times 3 is 9, minus negative 2, so that's 1/11th, times 3, 1, negative 2, 3, and again times 7, 1. And so at this point, some people like to multiply the vector by the matrix, or the matrix by the vector, excuse me. But if we're asked to find the inverse, and I will be looking for the inverse, then you'll want to do this part first. So again, some people say, well, let's go ahead and multiply these two because I don't have fractions, but I don't want you to do it that way. Besides, fractions never really killed anybody. So let's go ahead and find then my A inverse, which is 3/11ths, 1/11th, negative 2/11ths, 3/11ths. I'm multiplying that by 7, 1. And now we have to do math with fractions, which is good for your mental math abilities. So this is 3/11ths times 7, so 21/11ths, plus 1/11th times 1, that's 1, oops, not over 22, 1 over 11. And then I'm going to do my second row. Negative 2/11ths times 7 is negative 14/11ths, plus 3/11ths times 1 is 3/11ths, which means my solution, 21/11ths plus 1/11th is 22/11ths, or just 2. Negative 14/11ths plus 3/11ths is negative 11/11ths, which is negative 1. So there is our solution. Here are some provable facts about invertible matrices, and I'm going to leave those proofs to you. You, of course, can find them in your textbook in section 2.2, or you can certainly Google and find someone else to explain the proof for you. But I would challenge you to see if you can prove these on your own. So first fact, if A is invertible, then the inverse of A is also invertible, and the inverse of A is equal to A. The second provable fact, if A and B are n by n matrices, then so is AB, the product of A times B, and AB inverse is equal to B inverse times A inverse. And the last, if A is an invertible matrix, then so is A transverse, and A transverse inverse is equal to A inverse transverse. So that one can get a little bit dicey, but as we can see, these are all things that can be proved, and I challenge you to do that on your own.